Yeah, thanks a lot, Philip. And first of all, I would like to start by thanking Natasha and Sergei for bringing us here to this wonderful location. So I think they should get a round of applause, yeah? Okay, good. So my talk will be about light matter control of quantum materials, as Philip already said, and we've already had, I guess, last week, which I missed, a number of talks on related subjects, and also, for example, yesterday we heard Philip's talk, or another talk, I think, on the topic of Floquet engineering was already mentioned. We also heard a little bit about cavities. I think Peter was talking about cavities yesterday in a slightly different context. Okay, and this is a lecture, so I'm supposed to speak for 60 minutes or so. I understand that this is geared more at the students. I will try to keep it simple and accessible, also in view of the fact that maybe many of you are tired. Let's see. So I don't need to get through with any material. It's stop me anytime. Okay, so let's see. Does this work? Okay. So really, we already saw Dragan's talk this morning. Let's see if it works. Better. Okay. We saw Dragan's talk this morning. Dragan, are you here? You are. Yes. So allow me to briefly summarize what Dragan told us in his talk. So essentially what Dragan was saying is that we should take the Wikipedia logo. Okay, das is a bit, okay, let's see. Hit it with a hammer, yeah? Then we just create some random state. Then we have a lot of time to drink some tea or coffee. And eventually we end up in a situation where, okay, the system is, this is more or less a summary of what we heard this morning, right? And there were many orders of magnitude of time involved, and there's also back some questions. There's some puzzle about these STM data, for example. And then Dragan is happy. And okay, I would like to make a contrast in the second lecture of today. I will talk instead about very different timescales, more about the coherent dynamics and the sort of the hybrid state between light and matter in a material, and the focus is on dynamically establishing quantum correlations rather than randomizing an electronic system. So this is interesting in its own right, and it's very useful and very exciting and creates a lot of puzzles, as we saw. But my talk will be on a different subject. Okay, good. So the question, the overarching goal, the motivation behind this is, can we employ light-matter interactions to change materials' properties, to control them in a controlled fashion, right? And the first question that you might have is, when you think about light-matter interactions, is that if you, again, open Wikipedia before it's destroyed by Dragan, you look up the fine structure constant, which dictates the strength of interactions between charged particles and photons. And what Wikipedia tells you, well, first of all, it's a constant. It's given by all these constants of nature that, for all that we know, are independent of time, right? And second of all, actually, it's a small number. It's not tiny, but it's 1 over 137, so all the perturbative expansions, like these Feynman diagrams, actually work quite well. Quantum electrodynamics works. But here there's the paradigm of change. I want to change something, but I have to work with something that doesn't change and that is small. So how do I induce a big change with something that's small? Okay, and of course we know that there are ways around this problem. Essentially, I'd like to think about this schematically in this diagram with two axes. It's not a real phase diagram, but it's a way of organizing, an organizing principle. We can either use a laser, we have them, fortunately, and we know how to create a coherent state with many photons. So to basically add up many of these processes in a coherent way, and to generate, of course, large, macroscopically large electromagnetic fields that then can induce a big change in the material. So that's one way And this basically governs the first part of my talk. This is all the subject of non-thermal quantum materials, Philip's talk, for example, and also Floquet engineering, which I will introduce or maybe reintroduce if you already heard about it in this talk. But then, of course, there's the other extreme. If we instead think of a state with 0 photons or few photons, but instead find clever ways of cranking up the effective coupling strength between light and matter, and we know how to do this by confining, for example, light modes to some effective, very small mode volume. And this morning already there was the question when Dragan showed some cavity results, yeah, does the quality factor matter? I will argue that maybe it doesn't matter so much, but it depends on what you want to do with the cavity. Then we're in this other regime of cavity quantum materials, and I will introduce this and show you some examples. And as Philip promised, I will also talk about the connection, how these two seemingly very different regimes are actually tied together or can be tied together. And in fact, I would like to make the argument that in the spirit of Feynman, who said, you know, there's plenty of room at the bottom when you really go down to the very small scale. There's a lot of room in between, just like Dragan said about the time scales. There's also plenty of room here between these regimes. Yeah. And you know, of course, effects in the cavity QED regime that, for example, the Casimir effect or things like that are very small, seemingly small, very feeble effects, but they exist. And of course, you know a lot of interesting effects, maybe more in this regime of strong laser driving, and I think there's plenty of room in between. So that's the take-home message. Okay, so if you're really tired, you can fall asleep now for a bit. You already heard the main. Yes. Okay. And to read up a bit on this, we wrote like 2 review-type articles on both of these regimes, where the field stood like 2 or 3 years ago. This one in Reviews of Modern Physics, together with this gentleman Simon here, who also already gave a talk, and this one on cavity quantum materials. That's a very brief review of a field that's rapidly developing, and this is basically already half obsolete now, but maybe we'll write another one soon. Good. And in the spirit of Dragan, I will also use ChatGPT, of course. Who doesn't want to use it? Just play around with it. So when you talk about controlling quantum materials, let's say with a laser, well, the question is this a gold rush, and how do you illustrate how this works? So if you ask ChatGPT to create a picture of a laser physicist trying to dig for interesting states of matter, then this is what Chat comes up with. If you keep staring at it for a bit, it actually turns out to be really funny. First of all, look at the shovel here. The other thing is I actually tried unsuccessfully to tell it that the person was looking unsuccessfully for gold, yeah? And this is what an unsuccessful attempt apparently looks like. Okay, but actually you can make it worse, and you can ask for a theorist's drawing, and this is what happens if you ask for a theorist. Okay, so this is very bad, yeah? So obviously, first of all, I think there are 0 theorists in the room who look like this, and who work like this still, yeah? So, very outdated picture. Also notice that both of them are automatically male if you just don't prompt anything else. Anyway, good. So, more seriously though, how can we think about, how can we rationalize the question of controlling quantum materials? And it's more like a conceptual way of thinking about a problem is, take an equilibrium system. You know that, the properties of this given material, could be molecules, can be a solid, whatever you have, are of course controlled by the microscopic interactions that I think we have more or less under control. We in principle understand, if we had good enough computers, we could in principle compute all of this, right? With some caveats. Some classes of the most interesting materials maybe where still we need some method developments. But the properties are essentially governed by these microscopic interactions, by Coulomb matrix element, by hopping matrix elements, and so forth. And that's your material, right? And then you have a ground state, or you have some thermal state, or you have some quasi-thermal state, as Dragan told us. And then you measure it, and you're good. However, in an optically dressed situation, you can actually change these effective couplings, and I will show you how to think about the renormalization of a given coupling, also maybe also the fact that you can induce some hopping, for example, or some interaction by light that was not there in the first place. And that's actually where things get interesting, because that's precisely the regime where you don't just randomize and heat some system, but you really actually coherently change the Hamiltonian of the system, and thereby hopefully the wave function, and thereby hopefully the properties that you can then functionalize and use for some useful stuff that you get funding for and so on. Okay. And then, of course, these properties, what could they be? I mean, first of all, I will mention the example of band engineering through this Floquet light matter dressing. Then you can think of, for example, changing topological invariant. There were some talks related to topology also. Maybe you're interested in excitons. This is a very incomplete list, of course. Maybe magnetism. You can think of some strongly correlated states, such as the fractional quantum Hall state, or maybe superconductivity, if you like that, or charge density waves, or what have you. And again, this is the motto of the talk. I already said this. And in my talk, actually, this one of superconductivity, I think I will skip, but I will mainly motivate and show the concepts, the basic concepts in the cases of band engineering and some topological invariants. Good. I should also say, you know, being a theorist, if one is very honest, this field has really been driven by experimental progress. And for example, Dragan, you went over this a little bit fast, and you said, yeah, well, there are all these methods. First it was optics, and then it was, you know, photo emission and scattering, diffraction. But I think really this is where progress happens. Also in the spirit of Kai Rosnagel, whose talk I didn't see, but I know his colloquium talk, he was saying that the field is really driven by new tools. And then concepts, I think they're still important. Theory input is very important to understand and to guide some efforts, but and to solve puzzles. But I think initially the new tools really drive this progress. And for example, you have optical probes, you have scattering. If you want to look at some structure factors, you have transport, which is very important if you want to bring things towards like a device setting. Yeah, you want to do some on-chip measurements. This is what transport is good for. Scanning probes, of course. We also learned by Dragan this morning that this is very important to have probes that can look also at the right scales in space. And photo emission, and then there was a very nice talk, for example, by Andrea Damascelli, who also was a co-author of this very nice review article here that I highly recommend on the state of the art in terms of photo emission spectroscopy. Okay. And what ARPIS does, okay, I will show this in a minute. I think most of you know, but I will discuss a bit more in detail. And then, of course, we need the theoretical and computational progress and some schemes and some concepts in order to predict and understand and guide new efforts and to make a coherent effort. I think in this field, this is what is the most important. If you're an experimentalist or a theorist, you should always seek collaborations, and I think this is where the most interesting progress will happen. Good. So this is a brief outline of my talk. So I will first talk a little bit about Floquet basics, then I will talk about Floquet in solids, and then finally I will talk about the Floquet to cavity connection. Good. Okay, who of you knows what the Haldane model is? Which Haldane model? Yeah, okay. Do you know one Haldane model, at least? Okay. Who of you does not know what the Haldane model is? Let me ask the other way around. Okay. Everybody is just tired and nobody answers any questions. So there was no conservation of probabilities here. I couldn't see it. Fine. Okay, so just stop me if I explain things that are obvious to everybody. So Haldane came up with this model, this Haldane model. Okay. Back in 1988, of course, if you want to know what's going to be fashionable 20 years in the future, you should look at what Haldane is doing today, because he invented this model that goes beyond graphene, even though graphene wasn't even invented itself. It was theoretically predicted, the properties, but not synthesized, you know. So Haldane envisioned that if you take graphene and you add some additional terms that are not present in the material itself, namely an on-site potential, a staggered field that gives an on-site potential between the two sublattices, you can break, of course, inversion symmetry, or you can essentially generate a gap in the massless Dirac fermions. But you can also do it another way, namely by adding a complex second neighbor hopping that attaches a phase to by hopping along these triangles here, and essentially corresponds to something like a staggered magnetic flux through the unit cell. This is very similar to what Philip told us actually about this funny superconducting state. Yeah, this is sort of a similar thing. Yeah, you pick up a flux when you hop through the unit cell. These are fictitious fields, and they break symmetries of the Hamiltonian that are important to protect certain properties of the equilibrium system. That's the point. And the idea by Haldane and what he was really seeking was a model for a quantum Hall effect without a magnetic field. This is what we now call a quantum anomalous Hall effect, without an external, like Tesla coil magnet or something. And so basically in this phase diagram of broken time reversal and broken inversion symmetry, so one of these terms breaks time reversal, the other one breaks inversion. And graphene sits here in the middle. Both symmetries in combination, they protect the Dirac cone in graphene. And now you can break the symmetry either by breaking time reversal or breaking inversion, or both. And depending on which one you break more, in some sense, you will either end up in a trivial insulator or you will end up in a Chern insulator, and you can switch the property of the Chern insulator, you can switch the sign of the quantum Hall effect depending on the sign of this phase term here in the second neighbor hopping. Good. Now the problem is, as I already said, these are fictitious fields. Yeah. So if you work in cold atoms, you can introduce some fictitious fields by some suitable measures, but in solids this is not so easy. So therefore, there's this idea that in principle the second neighbor hopping, which is complex and breaks time reversal symmetry. So the important thing is not really the shape of this field. The important thing really is that it breaks the symmetry. And another thing that we know breaks time reversal symmetry is circularly polarized light. This was already discussed yesterday in a talk by, there was a talk in the afternoon about this. So I will just come back to this. But in order to understand how this works and how we can actually use a time periodic field in order to generate effectively a term in the Hamiltonian that's not there to begin with, I will introduce the concept of Floquet engineering. But before I do Floquet engineering, another question to the audience. Who knows what the Kapitsa pendulum is? Not so many. Okay. Some people know it. Okay, fine. So Kapitsa, was a Soviet physicist, very famous. He got a Nobel Prize for superfluid helium. But also he liked to play around, like he was a playful person, as all good scientists, I think, are, right? So he actually thought about how you could, when you have a pendulum, let's take a stiff pendulum, yeah? And we know that, of course, if we just have it hanging like so, it will just perform like oscillations around the minimum of the potential energy landscape. But there's also another, in principle, metastable position, right? The one where the pendulum shows upright. It's in the upright position. But we know any tiny perturbation will just destabilize that, right? So Kapitsa was thinking about that. Actually, mathematically, he derived the Lagrangian, he solved the equations of motion by some separation of timescales, and he figured out, just by pure thinking and math, apparently, at least that's how the story goes, that if you shake the pivot point, the suspension point of the pendulum fast enough at a frequency that is much larger than the eigenfrequency of the pendulum, then what happens is that the upright position will be stabilized and the downward hanging position will be destabilized. So he did the math, he did the calculation, he actually built this with an electrical shaver, which oscillates very fast. Okay, I didn't do like Peter did or Dragan the kitchen table experiments, but being a theorist, I did a numerical experiment. And this is what it looks like. Yeah? So if you add some damping, if you take the normal pendulum, it will just eventually do the normal oscillations that we all know. Instead, the Kapitsa pendulum will do this. Yeah? So it will defy gravity. It will actually, kind of overcome gravity and create a new potential. And of course, this is a classical example. The math you can do once you've heard classical mechanics, and this is a very nice example. And you can actually think about this in the context of Floquet engineering. So essentially, this is a high-frequency limit of Floquet engineering, an effective ponderomotive potential that you've created for this pendulum, and you've changed the effective free energy landscape of the pendulum in the presence of that very fast drive when you kind of integrate out, saying it in a more fancy way, when you integrate out the fast degrees of freedom. Okay, good. So this is how you can think of Floquet theory very simply. So the simplest example of Floquet theory is the Kapitsa pendulum, or one of the simplest examples anyway. But now let's think about Floquet theory a bit formally. Don't worry, I don't have so many equations. Only one or two Feynman diagrams to calculate later, but that's it. Okay, so you take a time periodic Hamiltonian. This is the time-dependent Schrödinger equation that you all know. And in fact, if you're in solid state physics, you all know the Floquet theorem. It's just called Bloch theorem. It's essentially the same thing. The Bloch theorem tells you that if you have a spatially periodic potential as a perturbation to your free particle, then you will get Bloch wave functions, and you will get an effective quasi-periodicity. You get quasi-momentum that is still a good quantum number. So momentum is conserved modulo a reciprocal lattice vector set by the periodic potential. And therefore, you can write an ansatz for your wave function. And now this is the same thing here in time. Yeah? You can write an ansatz for your wave function where you say it's essentially a plane wave e to the I kr times a Bloch function that is fully periodic in space. The wave function is not periodic. The important thing is that the wave function does not have to have the same periodicity, but it has almost the same periodicity, and that the part that's not periodic has the simple form of the free particle. Like it's a plane wave e to the I kr in the case of real space and momentum space, and it's a plane wave in the sense of e to the minus I epsilon t in the case of a real-time perturbation. Yeah, so this is essentially, if you only have this, this is exactly what the time-dependent wave function will look like starting from some initial state that is encoded in this stuff here. If you prepare a system in an eigenstate with energy epsilon, this will be the time dependence of your wave function, right? Just a phase factor, an oscillating phase that oscillates faster if your energy is higher, or slower if your energy is smaller, relative to the ground state, for example. So this is a relative phase factor, obviously. It's not an absolute phase factor. Good. But so now we have this phase factor. So this is in the context of a time-dependent drive, which does not preserve energy, but it preserves quasi-energy. So this is why this is called quasi-energy, very analogous to the quasi-momentum in the case of the Bloch theorem. And the rest of the wave function then does have the actual periodicity. Therefore, it can be expanded in the harmonics of the drive, e to the minus I m omega t, with prefactors, coefficients that are to be determined by solving an eigenvalue problem. So what you're actually doing when you apply this Floquet theorem and you make this ansatz is you're trading in the solution of a time-dependent equation for the solution of a static eigenvalue problem, but in a larger space. So you enlarge your Hilbert space. And this so-called Floquet Hamiltonian is, of course, related one-to-one to the time-dependent Hamiltonian. And then you have this extra term here, which is essentially you can think of the absorption of m photons from the drive, where m can be positive or negative. So you can emit into the drive, or you can absorb from the drive. Okay, that's the one-to-one correspondence. Good, so how do we think about this? And this is the ingenious part. So the Floquet theorem is old, and ingenious science is done by applying old knowledge to a new problem. And this is what Takashi Oka and Hideo Aoki did back in 2009, mainly Takashi, was to come up with an idea to use a Dirac fermion with a circularly polarized laser to create the Haldane model dynamically. And they, of course, only realized a year later that they actually created the Haldane model, but that's a different story. So let's start from a Dirac fermion. You all know what the Dirac fermion looked like. It has a 2x2 Hamiltonian. Forget about the A term here. has a 2x2 Hamiltonian that essentially is the Fermi velocity, which I've set equal to 1 as a good theorist. And then it has a kx plus iky. It has this intrinsic like chirality, although I know we have to be careful with chirality in 2D, but it's a different question. But essentially it has this winding, it has a Berry phase. So it's a kx plus iky, and the k bar is the complex conjugate kx minus iky, giving rise, if you solve this 2x2 Hamiltonian, of course, to this famous Dirac-Cohn energy momentum relation, right? And now we couple it minimally to a light field. Let's just think of a homogeneous field, A of t, vector potential. It's circularly polarized, so there's a phase shift between the x and y components. There's a cosine and a sine. And you just run this through the Floquet machinery now. And that's the Hamiltonian that you will get. This is truncated here for display, so there are higher terms. As I said, it's an infinite dimensional problem now with the Floquet space included, but for what we're going to discuss, it's enough to truncate. Okay, so what does this look like? So the sector here in the middle, this is just the original Hamiltonian, because the average of the field will cancel out for a linear dispersion, right? There's no nonlinearity in the dispersion here. So on average, the field will be will average to 0. The infinite frequency limit, you do nothing. But then you add the 1 photon absorbed copy. These are so-called Floquet sidebands. I will discuss them a bit more later. The -1 photon absorbed state. And the interesting stuff happens on the off-diagonals. And this is also where the polarization of the field will come into play. In the combination with the winding sense of the Dirac fermions, they lead to matrix elements that are non-zero only on certain parts of this 2x2 off-diagonal matrix part here. And the important thing is that now, if you start, let's say, well, okay, first of all, what this term does is, of course, you know this kind of stuff, right? You know bonding, anti-bonding, splitting in molecular orbitals. So if you bring two atoms together and they start hybridizing, you will open a lower energy state and a higher energy state. These are the A or MO theory. And you get a bonding and an anti-bonding state. That's precisely what happens here at the intersect between, for example, the main band and the +1 photon shifted band. They will hybridize and open a gap. These are linear in A. Yeah? This is just a direct hybridization, very, very simple. Then there's also this gap opening here in the middle. And that's a higher order effect, because obviously the yellow sector doesn't hybridize with itself. However, there's a second order effect. There's a second order process where the electrons from the center here, they can absorb a photon, go up to the red, come back down with this matrix, and then you're back. But that's second order perturbation theory, more formally said. But this is not the only way of getting there. There's another way where you first emit and then come back up. And now the point is that if you first absorb and then emit, or if you first emit and then absorb, these two processes do not commute with one another because of the breaking of time reversal symmetry. So another way of saying this is very simple. The green matrix and the purple matrix, they do not commute. The commutator is non-zero, and the commutator then gives a term, an energy difference between these two states here that you can end up in. And this energy difference is given by a squared divided by omega. It's a second order process. So this is, in the high frequency limit, again, this will scale to 0 in a 1 over omega fashion. Actually not, because A is related to the electric field like E over omega, so it's actually E squared divided by omega cubed. Yeah, so for this gap to be large, you want to be at low frequency, and then the high frequency expansion becomes tricky. So there's a lot to discuss here. There's some limitations to this, but the point is that the sign of the mass term is determined by the chirality of light. Yeah, so if you change the chirality, essentially you change the sign of the frequency, if you like. Yeah? Then you change from right to left-handed, you get a different sign of the mass term. And this is the hallmark signature of a quantum Hall effect. Yeah? If you change the sign of the effective magnetic field, you change the sign of the Lorentz force, if you like. Yeah? And you change the sign of the deflection of the carriers in a finite ribbon geometry. And then what was noticed by Kitagawa et al. In this follow-up paper is actually there's an exact mapping using this perturbative argument. There's an exact mapping of this Floquet Hamiltonian, if you've downfolded to the low energy sector, to the Haldane model that was written down 20 years earlier. So now we have a way of generating effectively this Haldane model without starting from the Haldane model. This is, I think, very nice. So now the question is, what can we do with it? I showed that these predictions were made in 2009-10, and then as it goes, I told you that the new tools are important, and experiments actually validate and drive the progress, really. So it turns out that the photonics people were faster. So Rechtsmann, he came up with an ingenious way of using a photonic crystal to emulate this broken time reversal symmetry. In a somewhat tricky way, actually, he created a three-dimensional structure. It's a two-dimensional photonic crystal, but you have these waveguides, and they have a corkscrew structure into the z direction. And if you write this, the ingenious insight by Rechtsmann really was that you can write the Schrödinger equation, the z dependence, you can treat it like an artificial time direction, and then apply a Floquet theory or something analogous to Floquet theory for the z dependence of the Schrödinger equation. And you end up with, if you started with an ungapped band structure with the Dirac form on a honeycomb lattice, you end up with a gapped structure if you include this winding in the z direction. Huh? They actually built these structures, yeah. And he showed that if you seed some photons into this, there's a chiral edge state associated with this the structure. So he actually could show that there's some chiral transport of photons along the edge of this sample. So this is very nice, but this is not Floquet engineering with a laser and a material, right? That's different. And then, of course, the cold atom people, they can do everything, or almost everything. They can't get to very low temperatures yet, but they can do many things. At the Haldane model with ultra-cold fermions was done in the lab of Tilman Esslinger at ETH Zurich in this very nice Nature paper. Notice that Gregor Jotzo, the first author of this paper, he is now, in the meantime, he switched and he's now working on quantum materials with lasers. So he came to the dark side, or to the bright side, depending on your point of view. He's in Lausanne, yeah, very nice guy, very smart. I recommend this review article by Mark Rudner and Nate Lindner if you want to know more about Floquet topology. There's also a very nice one by Takashi Oka and Kitagawa. I can give you some references if you want to dig a bit deeper into this. Good. But now, of course, the open question is, what about Floquet theory in solids, right? I mean, I've given you this nice spiel, and I've told you, in principle, this should work. I will discuss this experiment in a bit of detail, not too much, because it's the first experiment, in my view, that actually did some Floquet engineering in a material. But notice that there was quite some debate about this. So this was a Nature Physics paper back in 2020, in which basically what James in the lab back then of Andrea Cavalieri, he's now running his own lab, was achieving is that they were radiating a graphene sample with a laser, and then this is the cartoon. This is a bit closer to reality. So this is what the experiment looks like. What they actually did is they built a circuitry with these gold strip lines, and then they have a sample here. And here they put these so-called photoconductive switches, or Austin switches, which are some disordered semiconductor that you irradiate, that you hit with a laser pulse, and it has, due to the amount of disorder that you put in, it has a well-defined decay time of the photodoped charges in the conduction band, and creating a time scale of some few hundred femtoseconds. And that allows you to basically make this is a switch, yeah, so it's insulating initially, but if you hit it with a laser pulse, it becomes conducting for a few hundred femtoseconds. And for these few hundred femtoseconds, when it becomes conducting, this helps you launch effectively a current pulse, an electromagnetic wave, some kind of a plasmon, in the strip line that travels down the waveguide. To the strip line, it hits the sample. It transiently biases the sample for a bit of time, yeah, before it decays. And at the same time, you can irradiate the laser. So there's a light-induced current pulse that is sort of the probe, and there is a pump pulse on the sample, and they are of similar timescales. And this allows you to transiently measure a quantity that is proportional to the effective optical conductivity, or the more or less, I mean, AC-ish, but it's like a very small frequency type of conductivity of the sample, with a time resolution of below a picosecond. This is the fastest transport experiment that is done on chip at this moment, and they're pushing this in a new direction. If you want to learn more, look at Juani's poster here. They're doing new experiments with this setup. But essentially, this allows you to access the transport properties on the sample as it's driven by a laser. That's the new thing here. Okay, and what they actually detected was this. So this is the actual measured signal. This is the current. This is the Hall effect. Already shown the dichroism of the Hall effect. So this is for irradiation with one circular polarization minus the other circular polarization as a function of real time, as the system is irradiated by a few hundred femtosecond long laser pulse of some 200 millielectron volt photons. And this is for two different bias voltages along the y direction, along the perpendicular direction. So, you know, in a Hall setup, you apply a bias along one direction, a magnetic field along the perpendicular direction. In this case, there's no magnetic field. There's just a circular polarized light. And you measure the transport along the other direction, the transverse Hall type geometry, right? So for two different bias voltages that are relatively small, you get the opposite effect. So this has the right symmetry. And also if you, and then actually if you take into account the finite capacitance of the circuitry, so there's some technical details, but actually the real signal that you back out that happens of the current, that is much smaller in time. So that's lives for only the duration of the laser pulse, which is again consistent with the interpretation of a Floquet induced Hall effect, but that I will leave for a bit of discussion afterwards. Okay, it has the right symmetries, it has the right dependence on the bias voltage, it does not depend on the voltage along the same direction. So all the sanity checks are there. And then if you back out the effective conductance, Hall conductance, and plot this as a function of the laser fluence of the pump, you find a result that is, for different fluences, that is consistent with approaching a quantized value of 2e squared over h as you increase the fluence sufficiently. I should mention, and James wouldn't maybe approve of the statement, but there's the error bars here. I'm not quite sure about these error bars. Yeah, there's a lot of uncertainty about the size, the actual conductance, because you cannot directly probe the conductance. You have to infer the conductance from some additional considerations. But okay, at least it's fair to say it's definitely consistent with 2e squared over h. I'm not sure how certain you can be. And then if you plot this, then they can do the measurement as a function of the chemical potential. So you can bias the sample by gating, and essentially it gets this kind of three-peak structure at sufficiently large voltages. So if you park the chemical potential at the center of the Dirac cone, you get the sort of ideal situation of undoped graphene, and then if you change the doping level, it gets this kind of three-peak structure. And if you compare this with if you very suggestively overlay this with a Floquet type band structure for the different fluences, well, you can kind of think that, well, the effect might actually be related to the Berry curvature that is generated dynamically in a Floquet-like band structure as you drive the system. So the structure is definitely related to the frequency of the drive. Yeah? So if you look at the Floquet structure with the gaps that I mentioned before, it looks like this, and this is the measured signal here. Okay, so what are the observations? So let's take stock for a moment. There is a light-induced Hall effect without applying a magnetic field. It has the right symmetries. The Hall conductance at very strong laser fluence shows some result that is at least consistent with a quantized value, but I would, again, take that with a grain of salt. It has these peaks and dips that are reminiscent of the Floquet-induced gaps as a function of the chemical potential. But there's an open question of whether these are really Floquet topology effects, or to what amount are they Floquet topology effects? And we did some theory for that. Notice these papers here. So the answer is yes, but there are also more like semi-classical contributions from a population imbalance of excited charge carriers. That's, I think, pretty clear. And so the question remains a bit open to what extent this is really a proof of Floquet engineering in that material. But anyway, I think the technology, again, the tool developed to do this experiment really will drive new progress and is already doing it. So that's for sure. Okay, so there are other observations. I was mentioning photo emission earlier. There are other observations of Floquet physics in materials. And in fact, the first experiment in a material that showed Floquet-like effects was by Nugetic at MIT in 2013, and a follow-up in 2016 in Nature Physics, in which they really showed that if you follow snapshots of the effective band structure, of the light-dressed band structure during the drive, definitely at time zero you find these sideband-like effects. However, I should caution that, and I will come back to this later in my talk, there's another effect that is sort of very annoying if you want to hunt for Floquet effects, and the problem has to do with the experiment itself. Now, this goes a bit into more detail, but I'd like to tell that part because it's actually very interesting in some sense, is that when you take a sample and you irradiate it with a laser pulse, yeah, and then you do a photo emission experiment where you also come with another laser pulse and you want to photo emit electrons, yeah, the annoying thing about electrons that makes them useful on the one hand, but also very annoying on the other hand, is that they are charged. So they come out of the sample, they get emitted, and these charged particles, they see the electromagnetic field of the pump. So basically, they feel a ponderomotive potential, they feel a force of the pump pulse as they are already photo-emitted out of the sample. So in an ideal world, you would like to magically switch off the pump pulse in front of the sample and only have it inside. But this is what you just cannot do. It's just geometrically impossible. So what happens is that these final states, after the photo emission process has been done, they will also get dressed. They will also have shake-up states. Yeah, they will also have they have also sidebands. These are called Volkoff states, or this is called laser-assisted photo emission. This effect, LAPE, and it will generate features in your effective spectrum that you measure in the photoelectron detector that look eerily similar to Floquet states. Fortunately, okay, I will come back to this a bit later, they have a different dependence on polarization and such things. So you can actually distinguish the two. But the mere presence of the sidebands is not a hallmark signature of Floquet physics. So it could also be these sort of, the dressing can happen inside the sample, these are Floquet states, or the dressing can happen outside the sample, these are Volkoff states. In reality, you will have both. And you have to find a way of disentangling them. That's why it's important to have other probes that don't suffer from this problem. Yeah? Okay, I just wanted to mention this. I will come back to this in a minute. Yeah, yeah. Yeah, they are distinguishable. I will come back to this, but it's still tricky. So if you only look at, my point is that seeing sidebands is nice, but it's not real Floquet engineering in a sense. Also because the Floquet engineering about this gap opening stuff, the gap opening only happens in the Floquet state. So this is a unique signature of Floquet physics. The fact that you have replicas is not unique for Floquet. That's all I wanted to say. Okay. Yes. Yes. Yeah. About two photon. Okay, it depends on what you're asking. I mean, you think of two photon photo emission or something like this. Yeah, sure. I mean, that's also present. Yeah. But that's usually we distinguish them. We distinguish them because okay, you want to use different. You have a laser, and you have typically you have some low energy photons for the pump, and you have some much higher energy photons for the probe, with very different intensities, and that's how you want to distinguish the two, right? But you're right. I mean, there's two photon photo emission processes. In principle, ideally, you want to do a full simulation of everything, including all the lasers and so on, and then you can start to disentangle the effects. And this is in fact what we do. Yeah, with a proper theory. But you're right, I mean, the processes are all there, right? I mean, at the end, you do a measurement, and what comes on the detector is on the detector. And it can come from all the perturbations that you did to the sample, right? This is why I think theorists are not completely useless here. Yeah. Okay, so what about observing, the other question, I mean, this is the surface Dirac fermions in the topological insulator. But now I want to ask the question, what about observing Floquet states also on time-resolved photo emission? And this is an ongoing challenge to overcome decoherence. I noticed that I've been talking for way too long. So I will skip one entire part of my story because I also want to talk a little bit more about cavities. Okay. So what about graphene? The answer is here. In fact, just very recently, finally, I think we found Floquet states also in graphene, which turned out to be quite of a puzzle for a long time. So there was this light-induced Hall effect experiment, but directly in photo emission they were not found. And there were many arguments about why they were not found. For example, the decoherence and scattering timescales in graphene are just very, very fast compared to these TI surface states. But lo and behold, I think we found them in the group of Stefan Matthias and Marcel Reutzel in Göttingen. They now finally did an experiment, and the poor PhD student, he really had to measure very, very hard for 3 years and redo the measurements and measure the full polarization dependence for the probe and everything. And if you do a very careful analysis of the whole polarization dependence, eventually, including theory that can model both the Floquet and Volkoff processes and the interference of both of them, and then you do an angle dependence of the intensity of the sidebands around the Dirac cone, and this allows you to really nail down the fact that you've seen Floquet physics in graphene. I would also like to highlight that there was a story behind where the group of Nugedik, they did the same experiment independently at the same time, found the same consistent results, so these papers were submitted together at the end after some negotiations behind. But in any case, finally, I think now I'm convinced that Floquet states in graphene also exist despite these very short decoherence times and very strong scattering processes. But there's an outstanding question, namely the direct observation of Floquet topology under circularly polarized light that has not been done yet. This is linearly polarized light here. There's no breaking of time reversal. There's no gap opening at the Dirac cone here. Okay. And one possible resolution that this was suggested by Michael Schüler in this collaboration in Philip's group when Michael was a postdoc, is actually to use circular diachroism in terms of photo emission. This is probe diachroism, so you want to actually probe with right and left-handed circularly polarized light, and then you will see signatures of the induced Berry curvature that might allow you to see signatures of the gap opening under circularly polarized light, despite the fact that maybe the gaps are too small to be observed directly. And coming back to the light-induced Hall effect experiment, I think it's clear that some signature of Berry curvature must be there. It's just not clear, whether it can be spectrally resolved in photo emission directly. But this would be a way around. So I recommend a very nice paper by Michael, who was also involved in a lot of the theory, especially also the theory for this Floquet-Volkoff interference. Okay, good. So now I have, how much time do I have actually left? 12 minutes? Okay, good. So I want to at least advertise some of this. Okay, so the key idea in cavity quantum materials really is to replace these strong fields by a strong coupling. I already mentioned this. And basically a pictorial way of thinking about this is that in free space, you're losing a lot of photons. Yeah, so if you do a laser and you shoot it on your material, you absorb them, re-emit them, and they're lost. They're just gone. And of course, a very clever person will, in our today's world where recycling is an important thing, we want to recycle the photons. So we actually want to catch them and place a mirror above and below, and then they come back, and the same photon can interact with the material many, many times, and effectively this will look for the photon like effectively strong light-matter coupling. I should mention that there are very different cavity geometries, so a simple two-mirror geometry like the Fabry-Perot that Dragan showed this morning out of the Daniele Fausti lab is not the only way of doing this. And then actually, what I think will be even more interesting is to add a weak drive. So you can do this in vacuum, in the dark cavity, but you can also add a weak drive. The cavity will always be lossy. In this case, the lossiness of the cavity actually helps you to couple in a laser from outside. And then you're going to be in a situation of a driven dissipative system. And this will have very interesting dynamics, as we already also saw in Peter Littlewood's lecture yesterday, leading to very, very rich phase diagrams. And this really combines the best of both worlds. So this is the flexibility of the driven systems and the efficiency of the cavities. Good. So now one more pedagogical example, and then I will just do some flash in the spirit of a lecture, some recent examples. So I showed you this example already. And basically, now if the claim is that we can do Floquet engineering without a laser by using the concept of cavity engineering. So we have 10 minutes, and I'm sure you're still in the mood to calculate a Feynman diagram. Okay, so the goal is to induce a mass term by coupling a cavity with a circularly polarized photon mode to the material. How to fabricate that cavity is a different question, but let's say we can do that. And this was done by us, and then once we done the project, I realized that some Russians were always, they're always faster. In this case, it wasn't at least done in the 70s. It's not in Landau's book, but it was done in 2011. Maybe we can check. Unfortunately, they talked about creating a mass term in graphene, but they never mentioned the word topology or quantum Hall effect. Very bad. That was our, okay. And also our calculation, I think, is a bit more complete, but okay. Anyway, we noticed it after the fact. Okay, so this is our Hamiltonian. We start with the same 2x2 matrix, but now we couple it to a laser field. Instead of coupling to a laser field, we couple to a cavity mode, or actually two cavity modes to allow for a polarization degree of freedom. And in this case, we basically just treat the vector potential as a quantum field. Yeah? That's all you have to do. We use circularly polarized cavity, so we just plug in the correct polarization. And in this case, this amounts to the replacement in the Hamiltonian of the form kx plus iky minus a dagger with some amplitude that's controlled by the coupling strength to the cavity, controlled in turn by the effective mode volume, as I already said. Yeah? So this is essentially all you have to do, and then you have to find a way to calculate now the coupled ground state. So now you don't do Floquet physics, but instead what you do is you invent an effective coupling strength, and then you can calculate perturbatively, because this coupling, of course, in reality will be not so big. You calculate some Feynman diagram. Yeah? So you can calculate a self-energy. This Feynman diagram is the same diagram that you calculate in Migdal-Eliashberg theory to get superconductivity in BCS, strong coupling theory. But now we calculate electron-photon self-energies as a matrix structure. And it turns out that you get self-energies along the AA and BB components. That's already a good sign, because we want to have a mass term that will appear here on the diagonal. And if we calculate out these Feynman diagrams, which you can certainly do in your head, just do some Matsubara summation, some residual theorem, and some analytic continuation, you end up with these analytical expressions. So if you just do lowest order perturbation theory, this can still be done analytically. And if you take the limit of k equal to 0, just look at the Dirac point, you find this result. Yeah? So actually, it's g squared over 2 divided by this denominator for the AA, and it's g squared over 2 divided by this denominator for the BB. Yeah? So this looks like a tau z Pauli matrix term. So there will actually be a gap that is of this form, and the weak coupling limit, it actually is precisely g squared divided by omega, which is a0 squared divided by omega, with the Fermi velocity in between. And in fact, we wrote in this paper that this is a remarkably close formal analogy with the Floquet high frequency expansion that I showed you before. Remember the second order process, a squared divided by omega. This has the same form. But the meaning of the quantities is different now. Yeah? So there's no classical displacement field of the laser, there's really just quantum fluctuations. Those are enough. And they will create a Haldane gap if you calculate the spectral function. You can do this for different temperatures. I will skip ahead a little bit. Then we can do this sort of self-consistently. Oops. This is some numerics. And then you will actually also see some sidebands. But they have a different structure than the Floquet one. So it's not completely the same as Floquet, of course, but it's remarkably similar. At least some salient features are remarkably similar. In particular, of course, this gap opening is very important. Notice that there are no sideband hybridizations because you can't absorb from the dark cavity. You can only emit into it, right? Huh? Oh, there's a gap everywhere. The gap is just very small because it scales like g squared. So this is the most realistic case. So realistically, there will be a very, very small gap. Okay, we did some estimates. Okay, if you take the right cavity and the right frequency of the cavity, you might be able to observe a quantized Hall effect at some very, very low temperatures. In reality, this will be actually smaller because we copied a wrong number from a paper that was incorrect by Jerome Feist's group. Okay, I can tell you all the details. So I think in reality, this probably have to rescale that axis by another factor of 10 maybe. But okay, that's sort of details, yeah. Okay, so I have almost no time left, so let me just advertise the review article that we wrote about the subject. There's a lot going on in this field. You can have all kinds of different cavities. For example, you can have these split ring resonators. You can have stuff like this. You can also have surface plasmons, and I think this will be a very important avenue for the future to basically design new cavities. This morning we had the question by Gabe about the quality factor. So the lab of Frank Coppens in Barcelona, they actually demonstrated a new cavity with hyperbolic polaritons with reasonable quality factors. They're not great. I mean, between 50 and 100. But more importantly, a very small normalized mode volume. Therefore, very high effective field strength. So the field amplitude is more important, I think, for many things than the quality factor of the cavity. I would also like to mention the lab of James McIver has also created some van der Waals heterostructure-based cavities. This is still a very recent work that we did. Okay, so a lot is going on in the field. So let me, in the spirit of time, skip ahead. Maybe just very briefly advertise two recent experiments. One was already advertised by Dragan this morning, or maybe we advertised a few more. Sorry about this. Ah, yeah, okay. So this one, this is in the group of Jerome Feist at ETH Zurich. Here we had this example of the McIver lab of light-induced topology. In fact, in Jerome's experiment, they probably rather destroy topology by a cavity. They take a quantum Hall system, gallium arsenide, at very, very low temperatures, and they place it into a split ring resonator, and they find a shift and some changes of the quantized integer and fractional quantum Hall plateaus. This is still, I think, poorly understood. They have a follow-up experiment that was just put on archive, I think, and submitted very recently, where ingeniously they find a way to actually change the distance of this antenna from the sample and look at the full distance dependence of these quantum Hall levels, which is very interesting. There's also cavity-induced superconductivity. This is super highly debated. So if light-induced superconductivity, I don't know if anybody talked about this at the conference, it was mentioned as a motivation in some talks. So if light-induced superconductivity is already highly debated, then cavity-induced superconductivity out of the lab of Thomas Ebbison is even more debated. But it exists. This is what Dragan showed us this morning, the cavity-controlled charge density waves. I think this is really the new frontier, and there will be hopefully there will be much more progress at the next Impact conference in 2028, I guess. Every 4 years? 6? Every 2 years. Okay. So at Impact 2026, there will be even more. It's only every 4 years in Cargèse, maybe. No? Okay. Anyway, and just to advertise this, I think this crossover here is the most important, the most interesting regime. Let me finally, highlight also another a very nice perspective article in Nature by these scientists here, where they talk about strongly correlated electron-photon systems. So there are a lot of different regimes bridging quantum optics, plasmonics, and material science from weak to strong coupling. Correlated materials, uncorrelated materials, metals, semiconductors, superconductors, what have you. So many playgrounds, and there's a workshop going to happen next year at KITP that I'm co-organizing with Martin Klaas, Mohammed Hafezi, and Suzanne Yellen in this very nice location, where we hope there will be an interesting interface between different communities, again, from quantum optics to material science. So stay tuned, and with this, let me just summarize. I didn't even talk about this part, but it's okay. The funding is important, and thank you very much for your attention.